Yeah.
Okay. It should be recording now.
Okay. Perfect. Okay. Hello, everyone. Thanks for coming. This is our first professional development seminar, and Dr. Sid Paul. Um, he's very kind, and he came here just to give us a very interesting talk about sustainable soil and agro ecosystem management using geoinformatics. So just a little introduction for him. He joined Purdue at June 2023, I think that's right. And he is assistant professor of geospatial science here at Purdue, of course. And his research explored how human-driven landscape changes affect soil-related ecosystem services using Earth observation and geospatial data science. So today he will be giving a talk about how geomatics can help with sustainable management of soil and agroecosystem for enhanced climate change mitigation and adaptation. And he will also be introducing a course that is called geospatial informatics that is going to be offered on spring 2025. Yeah, I think that's it.
Okay.
Thank you.
Yeah, thanks very much for having me today. I heard that I was asked to give this seminar since there are some GIS research interest among the grad students, and I really hope it extends beyond my research group because that's what my grad students told me. So I'm happy to see some other folks here today. And I just realized this would be my first in-person seminar I'm giving at Purdue because during my interview, I had to do it online due to COVID. So thanks, EXO, for inviting me again. And a little bit about me, since I knew you already heard, I joined in June 2023. And before then, I was briefly a research scientist with the Government of Canada. I got my postdoctoral training from the Swedish University of Agricultural Sciences, obviously in Sweden. And I got my PhD from the University of British Columbia in Canada. But before discussing geoinformatics, which includes remote sensing, GIS, and spatial analysis, let's briefly talk about some of the grand challenges of the current world that we are facing. Globally, the demand for food is expanding at an alarming pace, and it is projected that by 2050, we have to produce 50% more food than what we're producing now. And that's putting enormous pressure on our land base. This map here shows the global cropland expansion over the last 20 years. And anything green on this map is stable cropland, blue is cropland expansion, and red is cropland reduction. And most importantly, the net primary productivity, which is shown by the graph on the top right corner, has been increased by 25% during the same period. So net primary productivity, or NPP, may not be a direct indicator of crop yield, but it is a measure of how the vegetation is performing. So vegetation health. That means if the NPP is increased, that means we either expanded the cropland or intensively farming the cropland to produce more food. And the same research found that 34% of this NPP growth has been attributed to the stable cropland. So that means we are really intensively farming these landscapes, which we have been farming over hundreds of years maybe. And as you can see in this map, South America and Africa, they have experienced the most cropland expansion during this 20-year period or so. And if we look closely at US specific study, this is what this map is showing here. So in the US from 2008 to 2016, cropland had been expanded at a rate of over 1 million acres per year. All the red areas in these maps are expanded croplands. This study also examined yield from these expanded cropland area and found that about 70% of this extended cropland did not perform very well. So they produced yield below the national average with an yield deficit of 6.5%. But these came at a higher cost, like cost of the disturbing the wildlife, biodiversity loss, loss of natural vegetations like grassland, and loss of or emission of carbon, and most of which came from soils. So talking about carbon emission, this animation displays the global warming since 1880. The research conducted by NASA found that Earth's average surface temperature was warmest in 2023. And the past few years have been the warmest of the last 140-year period. We have been experiencing record-breaking hot weather last several years. Each month from July to December are setting global record of high temperature. And we humans are mostly responsible for this unprecedented trend of global warming. By fossil fuel burning and improper land management, we're emitting greenhouse gases to the atmosphere and thickening its carbon concentration. Despite due to COVID-related economic shutdown in 2020, the global average atmospheric carbon dioxide concentration was 412 ppm, which is extraordinary. And the latest number in July 2024 is 426 ppm. So it is increasing. And therefore, climate change solution is at a now or never stage now. And to mitigate climate change, scientists have identified reducing greenhouse gas emission alone cannot help us much. We need to bring back the atmospheric carbon dioxide that we have emitted already. And luckily, we have a thin layer of soil blanketing the Earth's surface, which can store an enormous amount of carbon for us. So currently, we have about 830 petagram of carbon in the atmosphere, while only the top 2 meters of soil can store 1,500 to 2,400 petagram of carbon. And with careful and sustainable land management, soil can store and bring back a large amount of carbon dioxide that we have already emitted. And this is why in 2015, at the COP21 conference in Paris, the global community agreed on an initiative called 4 per mil. So that is increasing the soil organic matter stock by 0.4% every year. So which highlights the importance of soil organic carbon sequestration and led to the recent emergence of soil carbon trading market. But why the farmers would be interested in storing carbon in their farmlands? So soil organic carbon, or SOC, is not only a way of natural climate change solutions, but also it is a key soil quality parameter. So for example, SOC enhances water holding capacity and infiltration in the soil, which is very important for soil water dynamics and overall management. It also improves soil tilth, nutrient storage and cycling, and enhances resilience against different diseases, all of which contribute to better crop health and productivity. And provide effective solution for climate change adaptation for the farmers. So sequestering carbon, atmospheric carbon dioxide in soil can not only help with climate change mitigation, but it can also help with climate change adaptation. But the challenge is soil organic carbon are related soil health parameters. They are sensitive to changes in land use, land cover, and agricultural management. In this animation, I gathered time series Landsat satellite data to show the land use, land cover changes around Lafayette, Indiana. So capturing this landscape level variation is extremely important for effective decision making in sustainable land and soil management. And we need site-specific baseline data on soil, land use, crop, and climate to design an efficient system that can support soil and agro-ecosystem sustainability. And thankfully, such site-specific and efficient management can be achieved using geospatial data-driven approaches, that is geoinformatics. And in recent years, smart farming has been identified by the scientists as a key component of agricultural sustainability and sustainable management practices. Geospatial technology and digital data analytics enable site-specific precision land management, which support both economic and ecological sustainability. But what are the tools that made geoinformatics such a powerful solution these days? Any guess what you are seeing in this video? No guess? Okay, I downloaded this video last night, which is showing an almost real-time view of what we have in the space. So all these red dots you're seeing in this video are satellites. We also have rock bed bodies and debris, but there are hundreds of satellites out there which are collecting huge amount of data set for us to use for different purposes. And satellite data has been one of the main workhorse for developing geospatial data driving strategies over the last couple of decades or so. And if you closely look at these graphs, the graph on the left is showing some of the satellite missions from NASA, and the graph on the right is showing different satellite missions from European space agencies. And you can see over the last 5 to 10 years, there are like number of satellites that have been introduced and collecting terabytes of data sets every day for us to use. And then you add all these amazing UAV and drone technologies, global navigation system such as GPS, or proximal and in-situ sensors, right? So currently, this is a golden era of geospatial technologies and geoinformatics. And we have been observing an enormous growth in data gathering tools like this. Computing and data analytical infrastructures and facilities make geoinformatics-based digital agriculture a very powerful tool for site-specific and precision management, which can enhance the sustainability of our agricultural system. And another advancement is the digital soil mapping technique. So, which was possible due to the state-of-the-art geospatial tools that I just mentioned. And digital soil mapping, or DSM, can produce high-quality, valuable soil information at different scales. But they are slightly different than traditional soil maps that most of you are probably familiar with. So let's dig a bit deeper to understand how the traditional soil maps are different than digital soil map. But first, what is a soil map, right? So soil map is a two-dimensional document showing the geographical distribution of soils. The soil map shows geographical characteristics of diversity of soil types, soil classes, and different soil properties in an area of interest. In this background image, you see different soil map units are marked by different colors embedded within different polygons, right? And soil maps can provide myriad of benefits. It's extremely helpful for agricultural management, such as it can inform where your soil carbon content is low, or where you need to put subsurface drainage because the soil is clay textured, or answering some basic questions like if this land is suitable for agricultural production. We certainly don't want to farm a land with lots of rocks in it or really poor organic matter, right? So those informations can be gathered from soil maps, and they're also helpful for forest management, resource extractions like groundwater and so on. And these days, soil maps are being used for soil carbon credit assessment too. And this screenshot is from Web Soil Survey. You probably use this map for many purposes if you're sampling in the field or in different other cases. So Web Soil Survey holds the USDA Sargo soil maps. And all these orange polygons you are seeing in these maps are showing map units that provide information on different soil properties. And another excellent expansion of the USDA Sargo soil maps is Soil Explorer. This is a proud Purdue product. Our very own Dr. Darrell Schultz developed this tool. And Soil Explorer converted the web soil survey information to a raster-based map products using high-resolution, lighter digital elevation model. For example, here you're seeing the parent material maps for Indiana, and he developed these maps for the rest of the country. But these traditional soil maps, although being enormously valuable, they have some important limitations, which can be addressed and improved by new generation digital soil mapping technique. So how they're different? So for example, in traditional soil map, data is presented at discrete polygon. As you probably remember from my first soil map slide, there are like polygons of different colors, but in nature, soil does not exist that way, right? You cannot make a sharp boundary between different soil types. So that's one of the limitations. So now there is a spatial generalization may happen. So for example, in this map here, which is representing somewhere in Clinton County in Indiana, this big polygon represents an area of 1 square kilometer. So everything within this 1 square kilometer area has only one soil value, although there are like tons of variation between this within this area, right? So with the traditional soil maps, we cannot capture this variability. While with digital soil map, it produces continuous raster map products like this. This is one of my study area from a 54-hectare field in British Columbia, Canada, showing soil salinity distribution at 5 meters spatial resolution. That means we can see the variability every 5 meters. So this is important for site-specific management. And another, and also digital soil map can be produced at different spatial resolution. So if we want to make a farm level decisions, we may need a map at the resolution of 5 to 10 meter, right? But if we are talking about regional or national scale decision making, we may be requiring maps at 100 to 200 meter resolution. So this is an important difference between traditional and digital soil maps. And finally, traditional soil maps are derived from the mental model of the surveyors. So depending on the surveyor's opinion and expertise and interest, a delineation of a map product could be different. And we cannot assess that how different they are based between the surveyors, right? But in case of digital soil map, the maps are predicted using mathematical and statistical models. And therefore, we can assess the uncertainty of the predicted map products. And this is important for confident utilization. For example, if a map is predicted with an accuracy of 30% versus a map predicted with an accuracy of 70%, we can make informed decision how confidently we can utilize that map products. And this diagram shows a generic framework of digital soil mapping. So we put together a geospatial data set from different sources, and then we combine them in a model, but inform the geospatial data products with real soil observations. And one point to note that although there are some important limitations with the traditional soil map, they can be a valuable resource for static soil properties like soil texture, material, and those information could be utilized in the digital soil mapping model to improve the model accuracy. And another advantage I would like to highlight about digital soil map, we can gather satellite information, for example, at different time steps, right? So we can see the spatial variation as well as the temporal variation. What happens, changes over time could be captured using digital soil mapping models. So as I mentioned, with continued advancement in data gathering technology, computational facilities, and this sort of new generation soil mapping technique, geoinformatics is really powerful these days, and we should be utilizing them for effective management of our soil and ecosystem. And I certainly take advantage of these techniques in my lab. So in the next few minutes, I'll describe a couple of my previous research, and then I'll briefly introduce some of the new project that my students and postdocs are conducting in my lab. So this first study is from Lower Fraser Valley in Vancouver, Canada. This study area, Lower Fraser Valley, is one of the most dominant agricultural regions of the province. It produces more than 50% of the British Columbia's agricultural production. And think about British Columbia is about 10 to 11 times larger than India. So it's a really large area, and the tiny bit of few thousand square kilometer landscape produces 50% of its food. So as a result, over the few decades, Lower Fraser Valley has been intensively farmed and experienced a substantial change in land use land cover, which might have caused a sizable loss of soil organic carbon. And on top of that, climate models predicted by 2050, there will be about 1.8 degrees Celsius increase in temperature and 7% rise in precipitation. And the type of the soil we have in this region is really poorly drained, and with this much rise in the temperature, precipitation may cause a significant issue for soil drainage management. So developing a site-specific management strategy at field to landscape scale is an immediate priority for this region. So in this project, we looked at the spatiotemporal dynamics of soil carbon, land use, land cover, and climate across the valley. And this diagram summarizes the overall approach we used in this study. We used time series Landsat images to track the change in land use land cover from 1984 to 2018. And then we combined the same set of Landsat data with soil survey variable, climate data, and topographic information to predict soil carbon at different time steps during the study period so that we can understand the spatiotemporal interaction between these components. And this is what we came up with. This map shows the absolute change in soil carbon from 1984 to 2018 at the top 15 centimeter of soil. And anything green in this map is associated gain, which is hardly to see because they don't exist. And red is soil loss, yellow is somewhere in between. And I found that 61% of these landscape experienced SOC loss. Only 12% has observed some gain in SOC, and 27% remain unchanged. But overall, it was a loss of 5.8 megaton of carbon dioxide equivalent during the study period across the region, assuming bulk density did not change during this period. And this loss is about 2.5 times of British Columbia's annual agricultural emission, which is quite significant. And when we closely look at where these losses were, we saw that it mostly was in the annual crop that has not been changed during this period and being continuously farmed under similar cropping system. So that indicates it was a really intensive farming practices that contributed to some of these or significant portion of these SOC losses in this region. So in this graph, the box plot, or in this block plot, all these black dots are showing mean. And you see the 25 percentile and 75 percentile changes with the error bars. So in some cases, we saw some gains. Some cases, there are some losses, but overall, the mean SOC was always on the decline side. But we also observed some hope with some of the practices, like annual crop, when annual crop was rotated between grassland, or annual crop was converted to perennial cropping, which is blueberry production in this landscape. They started showing some SOC gain, and we hope that probably in 1 or 2 decades, we may observe like net gain for these practices. But so from this research, we identified specific land use management that are responsible for SOC gains and losses, and also pinpoint the farms where the most losses or gains are happening so that farming decision can be informed. And let's go to Europe now. Let's see a project in Sweden. So in this project, we used geoinformatics to map soil wetness across Sweden. Accurate soil moisture information is extremely important, but really limited as well. And in Sweden, another important aspect of high-resolution soil wetness or moisture information is to utilize them for effective restoration of drained wetland. And Sweden is one of the most intensively modified boreal landscape in the world. So more than 80% of the channel network in Sweden are modified. So only less than 20% of the channel network across the country are natural, and the rest of them were man-made by draining the wetlands of the last 100 years or so. So recently the government has been putting a lot of effort to restore these drained wetlands, but they don't have specific information where those drained wetlands are and how the soil wetness varies across the country. So this is what we try to develop in this project. And this is the soil wetness map we developed across the country at 2 meter spatial resolution using laser scanning data or LiDAR data. There are like 5 different soil moisture classes, as you can see here. And we then developed multiple other products from this map. For example, one of these products was where we compared the soil moisture map with the thickness of organic soil thickness, which helped us map peat and mineral soil distribution across the country. And with this map product, now the government knows where the peat soils are and where they should go to implement wetland restoration activities. And then we also, as I said, so we reconstructed one of our LiDAR-based topographic map or digital elevation model to predict what was the natural channels in this landscape. So this is what the Sweden looked like in one of its watersheds, probably 100 or 150 years ago. And this is what it is now. And anything other than blue in this map is all man-made. People were paid money that period, and whenever they felt lazy or don't have anything to buy food for, they went to dig some drains. And this is what contributed to this landscape. So identifying those drainage, man-made drainage network was really important for the government for restoring these drained areas. And these map products are also helping digital forestry activity and digital agricultural activities as well across the country, because these are 2-meter high resolution products. So taking all this experience from different countries, I now established the GEMS lab at Purdue. So geoinformatics, ecosystem management, and soil sustainability lab to develop and apply geoinformatic-based approaches to study soil and agroecosystem at field to landscape scale to help with climate change mitigation and adaptation. So in the next few slides, I will introduce work of my students and postdoc who just joined me in the last 5 to 6 months. So don't get excited to see some results here. We don't have any results at this point. So 2 of my students, Omia, who is here, and Li Jiang, they're working with data sets from different Purdue Agricultural Center. And Omia is specifically looking at historical data set from Purdue agronomy firm Acre, while Li Jiang is collecting new data sets from 4 packs, Acre, TPAC, DPAC, and CPAC to perform benchmark soil health analysis between resilient and status quo or like current conventional agricultural management practices. So this is a long-term project or research trial being set up by a group of Purdue researchers across different departments. And Li Jiang will be collecting few hundred soil samples in the next few weeks. So he'll be a busy man. And so just a bit more information about Omia's project in Acre. So Omia is looking at data sets from 2016 to 2024 to model the spatial-temporal interaction between soil organic carbon dynamics and crop yields. For example, this map is showing dense soil sample grade in Acre that the Acre team has worked on from 2021 and 2023. So we'll calibrate an initial model using this data set, and then we incorporate different geospatial information at multiple time steps so that we can predict the trend of SOC changes over the last 10 years or so. And Omia is also collating spatial yield data that was gathered from the harvester at Acre. We expect that integrating this large-scale, multi-year data sets of soils and crop yield will help us identify some trends in how these 2 properties are interacting with each other and help us answer questions like which farm-level management practices are leading to SOC gains or losses, or question like if the gains in SOC or carbon credit are really converting to crop yield. So stay tuned for those results, which Omia should be working on in the next year or so. And my postdoc, Fitsum, who just joined 3 weeks ago, and he's still figuring out the Indiana weather. He landed here from Florida, showing up in the field with his shorts and beach t-shirts. So Fitsum became a part of a big project led by Dr. Richard Rui at our department. And this project will assess soil health in organic farm across the state. And Pearson will be developing geospatial models to understand how different organic practices are impacting soil health parameters at selected farm across the state. And finally, my other student, Nelson, who took a different route. We all love making beautiful maps and colorful maps. Nelson do too. But he thought he would be researching on how we can identify optimum location for soil sampling that will help not only for soil health assessment, but also for doing digital soil mapping work. So our landscape is highly heterogeneous, as you were seeing in this video, and capturing this variability during soil sampling phase is critical for successful modeling and site-specific decision-making. So Nelson's work will contribute to that. So our general notion is that if we increase the number of sample points, that will better capture the spatial variability, but that will also increase the sampling efforts and cost. And we hypothesize that there is an optimum point after which increasing the number of points may not help much with capturing the spatial variability. So Nelson's work will try to identify and satisfy that hypothesis. And there is a small body of research which have done work on sample design optimization. So Nelson is currently conducting a literature review to identify those techniques. And then he wants to develop a prototype tool where anyone, especially the farmers, can draw a polygon in that tool, and our tool should pop up with optimum sample locations for them, so that they're not, blindly selecting some spots for their annual soil health investigation. And finally, my other student, Avradip, who just came here with an Indian government scholarship and will be here for a year and a half. And his project focused on the sustainable soil management in the Indo-Gangetic Plain. He collected extensive data set from a large number of farms, as you are seeing here, across the Indo-Gangetic Plain. And now at Purdue, he's working towards developing two products. In the first product, he will be using cell phone images to predict easily measurable soil properties. That's what he says, easily measurable. So some of the common soil properties, and we are hoping it's going to be a really cost-effective approach for the farmers in developing countries. There is some ongoing research in this phase, but we are hoping that with his data from a large number of farms in the Indo-Gangetic Plain, we should be able to calibrate an excellent model using deep learning tools. And then he will also develop an AI-based decision support system to help the farmers of the Indo-Gangetic Plain for making soil health management decision. And here we are hoping to utilize time series satellite data and different AI models. So as I said, all these projects are at their infancy. So we're hoping in the next year or so, I or my students will make multiple presentations to make you updated on our products. And finally, to my teaching program at Purdue. So I am starting a new course this spring, January 2025, and guess in what topic? Right? Geospatial informatics. So the course is already in the system. If you're still thinking about taking a course, this could be a course for you. So my target groups are senior undergraduate and graduate students. And this is a few overview of the course. Like by taking the course, I hope student will develop advanced knowledge in geospatial science, emphasizing applications in soil, natural resources management, and forestry. And they'll explore cutting-edge techniques in GIS, remote sensing, and spatial modeling. And some of these I showcased through my research today. And this will equip students for the current trend of digital agriculture and site-specific management practices. So a quick overview of the syllabus. These are some of the topics we'll be covering during the lecture, like some intro lectures on geospatial informatics, talking about emerging tools, remote sensing tools. We'll be talking about cloud computing, geospatial data based geovisualization, And then for sure, I'll be talking about digital soil mapping and site-specific management. And there'll be like corresponding lab components for all these topics. And there are some prerequisites. So I talked to people across the campus, different experts in remote sensing and GIS, and I was told that we do have some introductory GIS courses and some really advanced courses. We need something in between, and that's why all these prerequisites are for. So there are like 3 introductory GIS courses identified that are taught on campus. So it would be helpful to have that courses done, but for grad students, those could be reduced based on the requirement and consent from the instructor. And yeah, these are some of the learning outcomes that I'm hoping from this course. So yeah, I really encourage you guys, if you are still thinking about taking a GIS course, this could be a course for you. And with that, I thank you all. I'm happy to take any question. And actually, all my funding agencies, and yeah, let's wait for the winter. It's coming, right? Any question for me? Yeah.
Whenever you work with satellite data, what is usually the source of the satellite data that you use?
Yeah, so say it again.
Like
What?
the provider of the satellite data?
Okay, who are they? So when I do research, I usually go for free satellite data, which are coming from different government agencies. So NASA and then ESA, European Space Agencies, and there are a few other providers as well. And there are a lot of commercial providers these days, like many of you know about PlanetScope satellites. So they do provide some free data downloading for new laboratories, for students, for researchers, but they come at a price. So I try to develop tools that the farmers can avail at a low, no cost. So I always go for free satellite data. And for many of my work, I like to use time series information, and what could be better than using Landsat satellite data for that? They have an inventory since 1984 for great quality data, and some really poor quality data since 1972. Yeah. Mm-hmm. Any other question? Yeah.
In your slide, you were doing or something like you talk about your digital soil mapping. So can you talk more about the calibration?
Calibration?
Yeah.
Okay, so we so as I was referring to Nelson's project, typically we put together some initial geospatial information like topographic information and NDVI type of information. And then we put this in a model to identify optimum locations for sampling. We go out to the field, collect soil samples, and then calibrate model using those field observations.
Are you calibrating your grid based with the in-situ data?
Am I calibrating my
Grid based data with the in-situ, or like how you are making?
So in most cases, we don't use any in-situ real-time sensors, but the soil samples collected using a grid or with a spatially optimized sample design, which is not necessarily grid all the time. It could be a stratified random sample design.
Or you mean like what the observed data, so you guys are taking with like kind of drone or something?
No. Just soil information, and then either we calibrate those information with the drone data or satellite data. Yeah, but this is another avenue for research, is that we collect high resolution drone data and upscale it at a regional scale using satellite data. So that's another option. So there will be 2 levels of calibration. So field observation with drone and drone with the satellites. That could be another avenue as well. But I have not explored that yet. Some forestry people are using that a lot.
And when you're dealing with the time series data, like how much uncertainty you guys are like, from one year to another, like?
So that's a very good question. So when we are talking about time series information, we are not only talking about annual time series, also within a year time series as well. So we try to collect data set from really early in the season to late in the season, so that we get reflectance from bare soil to vegetation, to what happens after the harvest, like if the crop residues are left, because that may contribute to the soil system, right? So typically for our case in Indiana, for example, we collect data set from starting in April to November or October, let's say. And then we do that for multiple years so that we get that. And when we collect those data sets, so when I'm comparing data from April, I try to stay within a window of a week so that those uncertainty could be minimized to some extent. But yes, there are some uncertainties for sure because satellite can't penetrate through the soils, right? So when we are talking about digital soil mapping, be prepared for some high uncertainty product at the range of 50% or 60% accuracy. While we are mapping like, crops or land use, we are looking at uncertainty in the range of like accuracy in the range of 90%, 95%, which is not the case for digital soil mapping.
Thank you. And last one,
Yeah.
so you mentioned about the spatial resolution for your digital soil mapping was 5 meters. So is it really used, can we use the data for the, farm operation?
Yeah, so these days with all these exciting drone products at a few centimeter resolution, so those are great for phenotyping type of research where we need to measure every leaves maybe, right? But for soils, there should be a fine balance between how fine resolution what we want versus how coarse it should be. So I think in my experience, I have seen if we go below 5 meter, sometimes there are like a lot of noises. So for example, we can, even if you do like ride a bike through a corn row, we can even see that in my model, right? But that not necessarily can explain the variability in soil. So those type of noise could be really problematic if we use a really high resolution data set from remote sensors. For LiDAR data, it's a different story, I would say. Any other question? Yes.
Yeah, the Purdue has a graduate certificate program in geospatial information. I don't know if like in the future this course is gonna be part of that list.
I'm already thinking about it. A few of my students bring that to my attention. So I'm gonna talk to the GIS group in the library who runs this program so that this could be part of it.
Nice.
Yeah. Okay. Yeah.
Thank you so much for that interesting talk. I don't work with any of these, but it looks so interesting. And I hope that many people can take your course.
Okay, thank you.
Interesting. So thank you everyone for coming. This was our first professional development seminar. We are working on doing more of these. So stay tuned for more. Thank you.
Thank you.
Recording?
Exactly.
Okay.
Okay.
Muito obrigado.
Yes.
Para dar almoço. Para dar almoço.
All careers?
Para